Good morning. Um, we are we're nearing another midterm. We're nearing halfway through the semester, so the semester is just flying by. But we're coming up on midterm 2, and so we finished all the chapters. I think that included chapters, 7, 8, 9, 10, 11. So looking at energy, momentum, and rotational motion. So let's take a look at some examples from previous semesters' midterms. So I've got a couple semesters, a couple of midterms rather, from some previous years from Physics 3A. And so let's go ahead and get started. So here's the first set of problems, 1 through 4. So same format as we saw on the previous midterm. We're going to stick with that throughout the course. So I think that worked pretty well. So 4 problems, individual parts A, B, C, D. Ooh, look, here's another A, B, C, D, E. Anyway, with separate parts. And then the individual 4 problems evenly weighted for the midterm. Let's go ahead and get started and take a look at this. So the first problem says we have a 60 kilogram person skiing down, a 20-degree slope. That's a pretty steep slope. The kinetic friction of coefficient, or the coefficient of friction, is 0.13. So that's the one that's relevant. The skier is sliding, not static. And so, but there is a static friction coefficient here, 0.19. But the skier's moving. So it seems like probably this is the one we use. And then we're going to let the skier come down a distance of 50 meters. Now it says draw a diagram showing all the forces, so hey, this is kind of a throwback to, we could have done this on midterm 1, right? Back in chapter 5 or whatever. Anyway, here is the force diagram. So here is the skier. Yeah, they look kind of like a block going down the incline. Now, I've gotten used to, at this point in the course, I'm just dividing up that gravitational force immediately into cosine theta and sine theta components. So here is the mg cosine theta portion, here is the mg sine, and it's the mg sine that's going to help drive, it is going to drive the skier down the slope. Now there's a frictional force, and it's kinetic friction, so we're going to be using 0.13, the kinetic coefficient, and the kinetic friction force then can be written as mu sub k times n. And n, from the diagram, I can see n and mg cosine theta are going to be the same value. So I can make that substitution. They're going to be equal to each other. So I'm taking out the n and putting in mg cosine theta. This expression then, the coefficient, the mass, the gravitational field, the angle, that's going to tell me how much kinetic friction we will have. So that's the expression for my kinetic friction, and I got my acceleration and velocity, arrows drawn, I put them away, they're from the object, they're not forces. Yeah, I think that's it. I think we got the diagram drawn. Now what we want to do is we want to calculate the work, also known as energy transfer, due to each of the forces. So I think in class we talked about this in lecture, and we've had some homework problems where we do this. We want to go through each force one by one and say how much energy is being transferred into the object or out of the object, or which forces are not transferring any energy at all. And so the work due to a perpendicular force is 0. So the displacement is along the incline. And normal force is perpendicular. That's an easy one. That's 0. And yeah, that counts on the exam. So don't come back after and go, but I left out the ones that were 0 because they were 0. No, right in the ones that aren't transferring any energy. So I can see here, n is perpendicular, mg cosine theta is perpendicular to displacement. Those two forces will not transfer any energy. Now mg sine theta, that's the force we're depending on to transfer energy into this skier. And so skier's going to start out from rest, and then the skier is going to go faster and faster and faster. So I'm going to take the force, mg sine theta, and just multiply by the displacement. They're both in the same direction, and that gave me 10,055 joules. I probably could have rounded a bit more on that. And then friction is taking energy out. So frictional force is opposing the displacement, and that means that I got to put a minus sign on that, and I put the minus sign in by hand, and then I wrote down the amount of frictional force I have, kinetic friction, and multiplied, so this is force, times displacement once again, but there's a minus sign. So it says, gravity put in the 10,000 joules, but friction took out 3,600. So what's the difference between the two? And it says, what will the skier's kinetic energy be at the bottom? Well, whatever the W net was will show up as kinetic energy. And so in this case, we started with no kinetic energy at all. And that means that if I take the 10,000 that came in and the 3,600 that left, I am getting 6463 joules is what that worked out to be. That is how much kinetic energy at the bottom. And then it says, what's the skier's velocity at the bottom? And what we're going to do is take the kinetic energy formula from chapter 7. Is this entirely chapter 7? Yeah, I think it is. So this is entirely looking at that first chapter dealing with energy and energy transfer. And there we introduce kinetic energy as 1/2 mv squared. I can take v as 2k over m to the half. It's always, well, not too surprising. When you flip formulas around, they just don't look as familiar. So students, k equals 1/2 mv squared, everybody's got that down. But when you flip it around, it's not as obvious. But that's the same formula, turned around, allowing us to solve for velocity. So 2 times the kinetic energy divided by the mass. Did we get the mass right? 60 kilograms. And then square rooted. Don't forget the square root. This skier is going 14.7 meters per second. That's probably 30 or 35 miles an hour. It's pretty good speed. After going 50 meters, 50 meters isn't that far, right? So this is just where you set your skis parallel. You're not, skiing back and forth or anything. You just set them parallel, downhill, and just start from rest, and then you just pick up speed. 14.7 meters per second as the speed at the bottom. Questions on any of that? And I'm going to say this is a good problem. Be prepared to do a force diagram, list every force, and identify how much energy is transferring from each force. Now, you could say, well, what often happens is students, I'm going to say chapters 4 and 5 and 6 are more intuitive maybe than 7 and 8. These energy chapters take a little getting used to. They're not so familiar. And so on a problem like this, sometimes students will go back and try solving them using kinematics and forces from earlier chapters. And I would say, practice these techniques because, this problem doesn't specify you must use energy calculations, but you should. Okay, certainly part B, you're going to have to understand energy transfers to understand why these formulas are telling us how much energy is transferring. The velocities and maybe the kinetic energy, you could solve those from earlier chapters, but practice using these new energy techniques because they're not going away. We're going to keep using them as we go throughout the entire course, throughout the entire year. We're going to come back and make use of these. Any questions on these, let me know. Problem 2. Problem 2 says that we have a worker lifting a series of packages from the floor and placing them on a shelf. So there they are. There's my diagram. Here's the person, there are the packages. They've got to be lifted up and placed on the shelf. Ooh, look, they're 14 kilograms each. You know, that's like 30 pounds or something. I think that's too much mass. Anyway, it asks how much energy, how much work is required to lift each package. Now, if all we're thinking in terms of is energy transfers, then we have to look at what are the differences in energy for one of those boxes up on a shelf compared with the energy on the floor. And that would be an increase, not of kinetic energy. They're at rest to start with, they're at rest at the end, but it would be an increase in terms of potential. So it says the work we would need to do would be equal to that increase in potential energy. That would be given by mgh. So mgh, and that would be 343 joules. So each box that gets lifted up onto the shelf now has 343 joules of potential energy, and that came from work done by the person. Okay, so this time it's kind of literal, the number of joules of work done. In part B, it says, okay, the person is able to lift 7 packages every minute. Boy, I hope that doesn't go on for too long, because you know they're 14 kilogram packages. So what's the average power? And on average, what we can do is say that that's lifting 7 packages, so 7 times 343 joules. The person's got to come up with this much energy. Now, power involves energy rate. So we divide through by the time, and now that becomes watts. So it turns out 7 times 343 divided by 60 works out to be 40 watts. So this person is operating at an average power, an average energy rate of 40 watts. Now it says, what happens? One of the packages falls off the shelf. What's the kinetic energy of the package right at impact, right as it hits the floor? Well, the 343 joules of potential energy is going to get converted into kinetic energy. So I can see that there's going to be a drop of potential energy, and that's all going to go to kinetic. We're ignoring air resistance. So this is how much kinetic energy. They then say how fast will the package be moving, and again, here is the same formulas. Here is my kinetic energy formula. Here is the kinetic energy formula flipped around in order to solve for velocity. That's going to be 2 times the kinetic energy divided by the mass square rooted, and this time that worked out to be 7 meters per second. And so that's a pretty good speed, huh? How high was the shelf? 2.5 meters high. So it's, yeah, this person's got to really reach too, huh? How do they do that? This needs to be a tall person. If they can reach up to a shelf at 2.5 meters, that's a pretty good height. All right. Yeah. Now, a lot of these problems are just taken from textbooks and different sources. I mean, some of them might change the numbers around. The 2.5 meters height makes me a little nervous, but that's what it says. So, and then finally, part E, it says, what happens to the kinetic energy of the package once it hits the floor? I guess it could have been more clearly specified. But we're trying to follow the trail of energy, right? We understand from Chapter 7, Chapter 8, energy is going to be conserved. So we should always be able to do some type of bookkeeping related to the energy and be able to account for all of the energy. So let's see, we did 343 joules of work, which turned into 343 joules of potential energy, which then, when the package dropped, became 343 joules of kinetic energy right before it hit the floor. And then it's going to be thermal energy, right? Chances are it just hits the floor and if you check the surfaces of the box, if you check the floor surface, you'll find that they feel warmer. We could get in some thermometers in there, some temperature measuring devices to find out how much thermal energy has been generated. Now there's going to be sound that's generated. We're just going to bundle that effect in with the thermal energy. The sound eventually will just make the air molecules a little faster, a little warmer, a little higher temperature. Okay, that wasn't such a, I hope that wasn't a scary problem. It's a less traditional sort of problem, but it is a good example in just following energy through a fairly simple set of activities. All right, questions? Let's go ahead and move on. So in problem 3, this looks like chapter 7, this looks like chapter 8, this looks like chapter 9. So I have a momentum problem. I have an automobile collision, so I have two cars coming together, they're colliding. Now it says that it's inelastic. It says that the cars actually stick together and skid, okay? They skid to a stop. And so they've both got their brakes on. What's the velocity of the two cars immediately after the collision? And then how much kinetic energy is lost during the collision? And then how much force is there? So that's a good set of questions involving momentum conservation. So let's take a look at the first one. What we can do is we can do a diagram. So I've got automobile 1 traveling north, and I've got automobile 2 traveling east. So the problem actually has been set up so that we probably want to do a top view. So we're up in a helicopter looking down at this intersection, and we're following the two cars as they come together and run into each other. Now they're going to run into each other, stick together, and slide off at that angle where V is located. And it says the collision, it's just a fraction of a second. It's just 0.600 seconds during which the cars crumple. There's a short time interval between when the cars first make contact until they now can be treated as one object. So let's write down the information. So the masses were given. Car number 1 is 1,800 kilograms. Car 2 is 1,100 kilograms. This is the big SUV running into the subcompact, or running into each other really. Velocity 1 here is what they say, 35 kilometers per hour. So we're using 35,000 meters per 3,600 seconds. That's 9.72 meters per second. And then the second car is going faster, 45,000 meters per 30, so that's 12.5. So we've got the speeds in here. So, you know, this one's going like 20 miles an hour, and this one's going like 25 or 30 when the collision takes place. Now, momentum conservation needs to be carried out for each of these directions. We looked at two-dimensional momentum conservation, and this is a two-dimensional problem. So I'm going to take the momentum that was in car 2. So now the momentum there was m2 times v2, and it was entirely in the x direction. So that's the momentum that we start with. The final momentum in the x direction is going to be m1 plus m2 times what I'm calling vx. So see that final velocity of both cars? That represents the velocity right after the collision. One thing to remember with these vectors, see where we have that vector velocity? That's not showing displacement. It's just showing the direction of the velocity immediately after the collision has taken place. So now it's going to have an x component and it's going to have a y component, and the x component is going to have, well, it's going to be Vx, and it's going to have a mass of m1 plus m2. So the x momentum after the collision equals the x momentum coming into the collision. Now in the y direction we have a formula that looks very, very similar, and that is the momentum after the collision in the y direction will be m1 plus m2 times Vy. And that's going to equal the momentum from before, which is m1 v1. So the problem's two-dimensional, but the good news is that because the two objects coming into the collision have exclusively, one has exclusively x momentum, the other one has exclusively y momentum, it's simplifying our formulas. Then after the collision, they're one combined object with components of velocity in the x and the y. So we can go through and solve this. We have the m1 and m2, the v1 and the v2. I can solve for vx, I can solve for vy. I'm using momentum conservation to determine what the components of velocity will be immediately after the collision. So it works out that in the x direction, what was the speed coming in? The car coming in from the x direction was at 12.5 meters per second, but when the two cars collide, that is now reduced to 4.74. The car coming in the y direction was coming in at 9.72. Now that one is not reduced nearly as much, right? This is M1, yeah, so the 9.72 has been reduced to 6.03. So we've gone from here to here, and then, yeah, okay. And it has to do with the masses. So one of the cars has, well, not twice as much, but almost twice as much mass as the other one. And so in the x direction, we are seeing the velocities reduced almost by a factor of 3. And in the y direction, it's being reduced to about 2/3. So that's because of those ratios of masses. All right, these are the components then of the velocity, and if we use Pythagorean's theorem, we can calculate what speed. Now this is immediately after the collision. Remember, right when the collision happens, both cars slam on their brakes and they skid to a stop, and that's where we're going to leave it at, I guess. And so this is really just keeping track of the speed immediately after the collision, and this is the angle they are headed immediately after the collision takes place. Magnitude, direction, okay? That's a very good, momentum conservation problem, one to step through and then come back and step through it again and think of why these are the formulas that apply for this particular situation. Now in part B, what they're following up with is how much kinetic energy went thermal, because that's what's going to happen here. Some of the initial kinetic energy is going to be thermal energy once the collision has happened. So let's see what that would be. The kinetic energy initially for car 1, 1/2 mv1 squared, 80,030 joules. I had rounded earlier, I put the 30 back in. And then for car 2, 85,940 joules. Now those two kinetic energies combined, it says that the two cars together coming into the collision brought with them 171,000 joules. So that's the energy that we start with. Now after the collision has happened, we can treat the kinetic energy, we can treat the two cars as one object moving at speed v. And putting the numbers in here, I got 85,300 joules. Now, I think it's all just a bit of coincidence here that all of these kinetic energies ended up being 85,000 something. It's easy to get mixed up when you have a bunch of similar looking numbers. I hope I didn't get mixed up. Again, if you catch mistakes that I've made in these, any of these examples, let me know. Anyway, I took the energy from before, subtracted off the remaining energy, and said that much is missing. That's how much must have gone thermal. So the before here is this number. The after is here, and the difference is 85,006. So everything came out at 85,000 and something, right? So that's now thermal energy. Now, in the last part of the problem, it's asking about what was the force of impact when the two cars ran into each other. There were large normal forces, and how could we estimate the force? Now, in order to estimate the force between the two cars, I have to look at one car at a time. I can't look at both of them combined. That won't tell me about the force between them. So I have to decide which car to look at. Now, I'm looking at these and I'm thinking, you know what happened is when car number 1 came in, it didn't have any X motion at all, but after the collision happened, it did have X motion. So I took an object with no momentum in the X direction, I exerted a force in the X direction on that car, and that force is coming from car number 2. So the two cars, in terms of the X direction, car 2 gets slowed down, car 1 picks up speed. This would be the easier object to work in terms of because initially it had no momentum in the X direction. So what I'm going to do is I'm going to say the force in the X direction is given by delta momentum over delta t. Now delta t, that time interval, is just what we call t up above. So I'm going to say delta t is the same thing as the 0.600 seconds. We're getting an average force here. These are just averaged. And the momentum for car 1 underwent a momentum increase of m1 vx. So that's taking the mass of the car, and it's taking this number. So to get the F component in the X direction, to get the F sub x, I just want to look at momentum in the X. And putting numbers into that, I ended up with a force of 14,220 newtons. Now, why are the forces so large? Because it's a set of large objects, it's an automobile accident, and it's happening in a very short time period. So because the collision is over very quickly, the forces, it turns out, are very large. And that's the number I got for the X direction. Now, in the Y direction, let's say this too. Remember, the force X acted on both of the cars. So when the cars ran into each other, M2 exerted a force on M1, giving it momentum in the X direction, and car 1 exerted a force back on M2, slowing down its Vx. All right, same thing applies in the Y direction. So in the Y direction, maybe it's easiest to look at car 2. So looking at car 2, we have an automobile that comes in, it's got no momentum in the Y direction coming in, but object 1 exerts a force in the Y direction, and that pushes car 2 so that it acquires momentum in the Y. Now, how much force would that be? Well, the force that car 2 experiences, pushing it in the Y direction, would be delta Py divided by delta T, specifically for car 2. So I'm going to do M2Vy, that's a Y, divided by T, and that works out to be 11,060 newtons. Now, again, the force is acting on both the cars. So when the cars run into each other, they exert forces in the X direction on each other. They also exert forces in the y direction on each other. So car 2, as a result of the collision, experiences a force of 11,060 newtons, pushing it into the y direction, and car 1 experiences a force of 11,060 newtons, slowing it down. So it now will not be going as fast in the y direction. So it's a combination of collisions in 2 dimensions. Now when I combine those using Pythagorean's theorem, it says the net force was 18,010 newtons, and the angle came from using a tangent. Now this is a different angle, so this is the angle at which the force is acting, and I should have put a force diagram in here, and that worked out to be 37.9 degrees. Now these are almost complementary angles, and I was wondering, should they be complementary? I kept quite a few significant figures throughout. I guess that's a good, interesting thing you could follow up on it. Do those two angles need to be complementary, or is it just kind of a coincidence that they came out close to being complementary? So is this round off that we're seeing, and the angles really are complementary, or is it just a coincidence? And I'll take a look at that too. Maybe there are reasons why the forces, it could be that the forces acting are perpendicular, maybe not, to the final velocity. I'm leaning towards coincidence right now, but we could think about that. Anyway, as far as the numbers that are here, be prepared to do collisions in momentum, whether they're inelastic like this one or elastic. We've looked at a number of examples of both in the lectures, in the homework. And then along with that, be prepared to do the kinetic energy comparisons. Okay, so I always feel like that's important. You've got to check students' understanding of momentum, maybe in 2 dimensions, maybe in 1. But you want to also be able to keep track of kinetic energies before and after. I think you'll find that's kind of a feature as you read through these midterm examples. And then forces. In Chapter 9, we took a look at how do we use momentum before and after to determine what the average forces were during the collision itself. Okay, we like to say that momentum conservation allows us to make a connection from before the collision to after without looking at the details, but going back and using these force formulas allows us to view some of the details of what the collision itself, what that collision looked like. All right, any questions on this one? And there's a lot of stuff here. Let me know. Let's take a look at problem 4, and then we'll come back and take a break. So on this again was one particular midterm 2 from, I don't know, a few years ago. Problem 4 is coming from chapter 11, I guess, right? 10 and 11. So this is a rotational motion. And here we have a projectile coming in linearly, right? It's following a nice straight line. And it sticks to this bar that's been set up. Now it says, if you read the problem carefully, which I always have to remind myself to do, it says it's a fixed axis in a horizontal plane. So that makes this a top view. So again, I'm hovering over this setup. It's a tabletop maybe, it's frictionless. I have this bar set up along here. There's a fixed axis, maybe it's a meter stick or something, and we've drilled a hole through the middle, and we're going to only allow it to rotate around that particular axis. So we now send a projectile in. Projectile is 50 grams. The stick that we've got here is 800 grams. That's a pretty heavy meter stick. And the projectile is coming in at 7 meters per second. And look, it's got the length of a meter stick. It's 1 meter in length. Now, in chapter 11, we went through and showed that, well, let's think of it this way. If someone asks you what's going to happen when the projectile hits, you're going to say, hey, that stick is going to start rotating. And then the question becomes, well, the stick rotating represents angular momentum. Where did that angular momentum come from? And what we decided in chapter 11 is the projectile coming in has angular momentum relative to the axis. So we're kind of anticipating that this collision is going to happen, and we can say that yes, this object coming in does have angular momentum with respect to that axis around which the object will begin to rotate. And so I've got to take that as the momentum mv times the lever distance. Now the lever distance here is going to be 1/2 of L. And so putting all those numbers together, the amount of angular momentum coming in, 0.175 angular momentum units, which are kilograms, meters, divided by seconds. Now in part B, it says what's the period of rotation of the system once the collision has taken place. And the collision is completely inelastic. So that little projectile is now stuck to one end of the, I'm calling it a meter stick, I guess. So in part B, what we can do then is say, I'm going to take this much. Oh no, I just realized this. Why did I not see this before? Okay, warning, I'm using big L to be the length of the meter stick, and I'm also using big L to be angular momentum, because that's what big L is. I apologize, I should not have used big L for the stick. I should have used something else. I think in lecture, in class, I always use little a. That would have been better. I have really, okay, so, all right, see, so you can define symbols, you can double up on the symbol definitions. So this L is the L here, this is the length. Let's see where else we're going to run into this. Maybe we're okay past this step. I don't think we use angular momentum again. So this one calculation of angular momentum, this big L, after that, every big L we end up with is the length of the meter stick. So 1/2 mvL. Now after the collision, it's probably going to be easier to represent the angular momentum as I omega. So the rotational inertia then will be the rotational inertia for the stick rotating around its center. And this is on that that kind of short list of objects that I'm going to say you should just have these written in your notes. So the rotational inertia is for a sphere, a cylinder, a hoop, a stick around the center, and a stick around one of the ends. Those are the ones that show up most often. Those are the rotational inertias I expect you to be able to have in your notes. Now, in addition to that, you should be able to use the parallel axis theorem to calculate the rotational inertia around an axis parallel to the center of mass. All right, so this is the stick around its center of mass, and then this would be the rotational inertia of the projectile now stuck on the end because it's mr squared, and r is 1/2 L. So I hope I got all this right. When I solve for omega, the angular velocity, I've got a factor of v. Now, there's a factor of L here, but there's two factors of L, which is length, on this side. That becomes v over L. This is 1/2 m. This is 1/4 m. This is 1/12 big M. Now, I multiplied through top and bottom by 12. This is what I ended up with. And then I started putting numbers in. I ended up with a rotational velocity of 2.21 radians per second. Now, Radians are great mathematically because that's the natural unit for angular motion, but they're not very intuitive. So, you know, a complete circle is like 6.28 radians, something like that. So that's like a third of a circle every second. Anyway, something more intuitive is the period. They ask us to calculate that. The period 2 pi over omega can be written as 2.84 seconds. Okay, it is what it calculates out to be. So that's a little more intuitive. So this thing's not going super fast. It's going, you know, it takes 3 seconds to make one rotation. And I think the reason for that, it's going pretty slow, and that's because it's 800 grams and the projectile coming in was only 50. So it's an object with a lot more mass that we are setting into motion, and it's not going super fast. Now, again, kinetic energies. So let's see what the kinetic energies would be. For the object projectile coming in, 1/2 mv squared, the projectile coming in has linear motion. I'm going to use a linear kinetic energy formula, and I get 1.23 joules. So on some of these calculations where I have enough space, I've shown all the work in more detail. I would advise on the midterm, just show, you know, all the detail as much as possible. Show your work. If I can see intermediate steps, so for example, if this number is wrong, I can see this formula, but I haven't seen the numbers go into the formula. So, you know, show the work as you go through. Show the steps, units as you go through the problems. Yeah, so I started off with 1.23 joules of kinetic energy, and then the kinetic energy after, again, is probably more easily calculated as 1/2 I omega squared. So you can see, switching back and forth between a linear formula for the kinetic energy and a rotational formula for the kinetic energy. So substituting back in for that, I ended up with 0.193 joules. So most of the kinetic energy went thermal. It asked for a ratio. Let's see. Calculate the ratio. Well, I put K over K naught. That ratio turned out to be 0.157, or 15.7% of the kinetic energy is left. That means, you know, 84% of the energy went thermal in the collision. Okay, so it's a good example. It's angular momentum conservation, one of the key concepts from chapter 11. Again, I think this is a very useful set of problems, and it's formatted the very same way that midterm 2 will be formatted, midterm 2 that's coming up. Any questions on that? I am going to go ahead and take a break. We'll come back from break, and we will take a look at another midterm from a different previous year.